a 3 by 3 matrix, 3 rows, 3 columns. Let B a vector, column vector, and let W be the set of all linear combinations of columns of A. So W is in fact span of the columns of A. We got 3 columns. Okay. The question is in part A, is vector B in W? W is the set of all linear combinations of the columns of A. That means, can we write B as a linear combination of the columns of A? I mean, same question. So all we have to do is just solve the corresponding augmented matrix. The columns are, okay, we are answering part A, 1, 0, negative 2, 0, 3, 6, 2, 3, 2. These are the 3 columns. We want to see if a linear combination of these 3 columns will produce 4. Okay, let's see. If we get pivot in each row, not in the last column by the way, in each row, then we are good. Or if this system is consistent, then we are good. Let's row reduce. So we want to make pivot and 1, I mean that's the case here, so this is 1, then everything below 0, so 1, 0, we want to make this 0. So work on R3. So R1 is same, R2 is also same, multiply by R3 means R3 plus, okay, with this one plus 2 times R1, right? Because 2 times 1 is 2, and negative 2 to 0, 6 plus 0 is 6, 2 plus 2 times 2, 4, so 2 plus 4 is 6, negative 4 plus 2 times 4, 8, negative 4 plus 8 is 4. Okay, so pivot in first column 1, 0, 0. Now we want to move on to second row, so we want to make this pivot, and that's 3. We don't have to make 1, but if we make 1, then that helps to make the number just below at 0. But 6, we can make this 0 without changing this to 1. If we want to change to 1, then we need to multiply by 1/3. That will be 1, 1, 1/3. I mean, that's fine, but then we'll introduce a fraction and subsequent calculations will be much harder. I mean, slightly hard. So we don't need to make it 1. So here is 6. Let's make this 0. That's the main issue. So R3 again. So R3, let's multiply this by negative 2. Negative 2 times 3 is negative 6, and 6 will be 0, right? So R3 plus negative 2 times R2. So here is 1, 0, 2, 4, 0, 3, 3, 1. Now 0 stays 0. 2 times negative 2 times 3, negative 6 plus 6, 0. Oh, same thing, 0. Negative 2 times 1, negative 2. Negative 2 plus 4 is 2. Okay. Now, as you can see, the bottom row 0, 0, 0, 0 equals 2. That means this system is inconsistent. Okay. If we do not consider the last column, then we don't have pivot in we don't have pivot in each row. Okay. So 0, 0, 0 equals 2. Because of this one, this system is inconsistent. That means B, the vector B, is not, we can't write B as a linear combination of the columns of A. Okay. So is B in W? No. The answer is, now from this one, inconsistent because of 0 can't be equal to 2. Okay, so B is, the vector B is not in W, where W is the collection of all linear combinations of the columns of A. Okay, part B, show that. So it's true. So we need to prove that the second column of A is in W. Okay, where W is the collection of linear combinations of all columns of A. Okay, second column is in that linear combination. So let me write in this way just to make this matrix A. The first column is, I can just say A1, second column A2, A3. Okay, A1, A2, A3, where A1, A2, A3 are columns of matrix A, or when we write in this way it's kind of obvious. And now the question is, the second column second column A2, that one is A, second column A is in W, means second column can be written as a linear combination of A1, A2 and 3. So A1 something times A1 plus something times A2 plus something times A3. We need to prove this. We can row reduce, by the way, same thing. Thus A2 goes in the last column, and same thing. Okay, we can do the same thing, but look at the second column. Second column is, how about 0 times first column plus 1 times itself plus 0 times third column. I mean, 0 times means this should be 0, this will be 0, so it will be just A2. So the row reduction is not needed. So in fact, any column is always in that W, which is the linear combination of all columns. Okay, note this one is true. So the second column A2 is in W. Okay, same thing for A1. A1 we would do 1 times A1 plus 0, 0. Okay, final.